Good morning. My name is Atakan Aral. I am a tenure track assistant professor of computer science at Umeå University, Sweden, and a research leader at University of Vienna, Austria. Today I will talk about neuromorphic edge intelligence for rural environmental monitoring. As you can see, there is too much terminology in the title, so I divided my talk into three parts. First, I will talk about rural environmental monitoring and its challenges. Then I will introduce edge intelligence as a solution to at least some of these challenges. And finally, I will present neuromorphic computing as a future perspective for IoT and AI-driven monitoring of rural environments. So let's start with environmental monitoring. According to UN definition, environmental monitoring is a tool to assess environmental conditions and trends to support policy development and its implementation, or to develop information for reporting to national policymakers, international forums, and the public, or to achieve real-time decision making, which is most relevant for this presentation. And real-time decision-making is enabled by the rapid advancement of Internet of Things and machine learning technologies. And this contributes to various UN Sustainable Development Goals. So in this paper, we review and compare several large-scale environmental monitoring use cases which focus on rural areas specifically. These include air quality monitoring, water quality, seismic activity, avalanche monitoring, nuclear explosion monitoring, agricultural systems, and oil and gas well monitoring systems. For brevity, I will talk about only water quality monitoring in this presentation. So, industrial facilities are often located in watersheds because they use river water for various purposes in their process. And they release the water back to the river through a wastewater treatment plant. Unfortunately, these plants are prone to failures, and recently there have been several disasters, environmental disasters caused by failed wastewater treatment plants. These are just few examples. This one is from Kokemäki River in Finland. The other one is from Poland, Vistula River, and the most recent one is the Oda River on the border between Germany and Poland. So what is common to these disasters is that pollution was detected too late, after many hours, if not after days. So in this project, actually this is a project I am leading at the University of Vienna, we are building tens of measurement stations in the downstream river network and collect continuous water quality data. This data is then processed in real time by a machine learning based algorithm that models the river and predicts approximate location of the source of this pollutant. I will revisit this slide and we'll talk about where the algorithm runs. For now, you can ignore this edge server, cloud server communication. But once we detect the pollution and its source, we aim to send a warning signal within minutes so that an environmental disaster can be prevented. This is, of course, a huge improvement considering the examples in the previous slides. In these examples, the discharge was detected after days or when fish or mussels were found dead. So this project is called SWAIN, Sustainable Watershed Management through IoT-driven Artificial Intelligence, and it is conducted by an interdisciplinary project consortium including computer and environmental scientists from universities and governmental institutes from Austria, Switzerland, Turkey, and Finland. The project is funded by the European Innovation Council, and as I said, I am the international coordinator of this project. You can find more about this project if you are interested on the website. But in the paper, we reviewed 6 other environmental monitoring use cases focusing on rural areas and identified these 4 common challenges in these use cases. The first one is the electricity access. In most use cases, electric utility is unavailable at the measurement locations because these are rural areas, and therefore sensors have limited or no access to reliable power sources. Second one is internet access. IoT sensor must transmit the measurements to a computational resource for processing. However, in all use cases, we noticed that they suffer from intermittent or no connectivity to wide area network. Of course, satellite-based communication can be possible anywhere on Earth, but in practice, this solution is too costly or too energy intensive. The third challenge in environmental monitoring in rural setting is failures, because rural deployment of IoT sensors complicates their maintenance and results in failure-prone infrastructures. Although these systems usually do not collect sensitive data, safety risks are generally high, as failures might result in, for example, undetected pollution or in a disaster. Finally, we have the sustainability challenge, and due to the especially large environments and wide dispersion of sensors, it's a challenge to achieve good coverage of the target environment. This requires high number of sensors, which undermines the sustainability in terms of costs, energy, and network use, and as well as ecological footprints, because many of these sensors contain batteries. So, to cope with these challenges, I will now talk about edge intelligence paradigm, in which a part of the computation capacity is deployed at the edge of the network, close to where data is generated. As a result, training can occur at these so-called edge servers, which have high bandwidth local area connection to the nearby IoT devices. So, to give an example from the previously mentioned SWAIN project, because transmitting the raw data from the measurement station to the cloud server is not feasible due to unreliable wide area network, we deploy edge servers near measurement stations, which collect data locally and train a local watershed model. And this local watershed model, of course, have to be synchronized with other local watershed models that exist in the monitored river, so they communicate with a central server periodically. Of course, the output of this training, the local training, these model updates or gradients or parameters, needs multiple orders less bandwidth than transmitting raw data. So a more formal definition of edge intelligence is that it makes most of the widespread edge resources to gain AI insights. So edge servers are located, as I said, closer to the data source. By closer, I mean in terms of latency or hop count. And this allows higher data transmission rate and lower latency. However, in this edge intelligence paradigm has also further challenges, continuing from the previously introduced 4 challenges. The first one is we call insularity, because training AI models at the edge results in data scarcity and insularity. It's because these models are fed with limited data from a narrow area. That's why the models might not generalize very well. For example, in the Swain project, as I showed before, each edge server models a part of the river and lacks a global view of the whole watershed. The second challenge is the available computational capability at the edge of the network, because when we compare this to a resource-rich cloud environment, edge computing lacks significantly in terms of computational capability, but also in terms of fan-in, which is the maximum number of input signals it can process. And a final challenge is parameter mismatch, which can happen between the target parameters and the parameters that can be sensed due to technical limitations in sensor technology. Again, as an example from the Swain project, we aim to detect micropollutants in the river, but state-of-the-art sensors can only measure conventional water quality parameters such as pH or turbidity. Therefore, we need AI-driven algorithms to map these parameters to our target parameters to resolve this mismatch. The last part of this puzzle is the neuromorphic computing parts, which I will talk briefly about. And this neuromorphic computing is motivated by the so-called end of Moore law. In the last decades, the performance of von Neumann computers started to lag behind the exponential growth in the generated data size. This is called compute data gap, and to cope with this gap, various innovative technologies that diverge from von Neumann architecture has been proposed. These include, for example, quantum computing, optical computing, or reservoir computing. However, the one that is most interesting for our use case, which is environmental monitoring, is neuromorphic computing. It is an architecture that mimics human brain, how human brain operates. And compared to a von Neumann architecture, a neuromorphic computer runs massively in parallel, and it doesn't have the separation of the processing and memory units. And this results in a substantial performance improvement. In addition, a neuromorphic computer is event-driven, and therefore there is no continuous clock, and for example, non-activated parts of a neural network do not consume energy. And this brings huge energy savings to monitoring systems for rare events, like in our case, in disasters. Of course, neuromorphic computing has different implications on different systems. In this case, I will talk about its implications on edge intelligence. First, it has higher performance with less energy consumption, so it can perform especially well for graph-based tasks such as spiking neural networks, graph neural networks, and so on. As a result, we could have less reliance on cloud for intensive tasks. We can already run complex neural networks at the edge of the network, which also allows us to control the system in a decentralized way. For example, we can avoid using a parameter server like in federated computing. Federated learning. Then a massive benefit of or massive implication of neuromorphic computing on edge intelligence is its energy efficiency, because many of the IoT devices used in environmental monitoring are battery powered or energy harvesting systems. So this benefits them significantly. And finally, it has larger fan-in, so it can process more IoT streams at the same time. Of course, it also has some disadvantages. At least initially, it requires error handling and maybe even approximate computing solutions, because it might be initially prone to failures. And also using a different architecture in the computing continuum might result in additional heterogeneity, and this has to be handled as well. So one research direction that I would like to mention here is distributed model synchronization. When we have multiple local models, they have to synchronize to form a global model. But this is difficult because of intermittent communication, low bandwidth, and failure-prone compute nodes. So this communication can be either peer-to-peer or through a parameter server. In previous work, we showed that with an adaptive and a learning mechanism, this complete synchronization might not be necessary, and updates from only a set of nodes is sufficient. Similarly, in the Swain project, we demonstrated that updates from only 40% of the measurement stations are sufficient for accurate prediction. However, none of these results are validated on neuromorphic hardware, so we need further research on communication-efficient ways of synchronizing partial models. So, in summary, this work introduced Neuromorphic Edge Intelligence as a promising solution to the challenges in IoT and AI-driven monitoring of rural environments. There are, as I said before, there are other proposals for non-von Neumann architectures like quantum computing, but neuromorphic computing is arguably the most mature technology. Therefore, the researchers in this area will be the first to face these identified challenges. So we expect that there will be high interest in neuromorphic edge intelligence research in the upcoming years. Of course, I didn't cover everything on the paper. There are two other research directions in the paper, and we analyze the interaction between these challenges and research directions, and also have further numerical analysis. So I recommend you to check the paper. So thank you very much for listening, and please feel free to contact me if you have questions, comments, or proposals. Thank you.